Alright, welcome back. This time we're still looking at heat conduction, right? But now we're going to look at the rod with insulated ends. So previously we looked at cases where we had ends of a rod where we had the same temperature, which in that case we had two ends with 0-degree temperatures. It doesn't matter what temperature it is, they were the same. So that meant we had no steady state solution, we only had to deal with transient solution. Then we had a case where we had different temperature boundary conditions, which you have varying ends, right? So then you have to worry about the steady state solution and the transient solution for heat conduction. Now we're going to have insulated ends, and this changes everything. It means we're going to have to redo our boundary value problem. So I'm going to go through the whole entire heat problem again because things are going to change now, simply because of the reason is we're going to have Neumann boundary conditions, kind of associate anything insulated or anything with no flux, we'll call it. So let me write that definition for this. Insulated means no heat flux. How do I want to write this across it? No heat flux through surface, I guess. Which basically means no heat can escape or leave through the boundaries. A typical misconception is that it means there's no temperature change, but that's not true. The temperature can still change. It just means that as the rod changes temperature, the ends are never going to reach an equilibrium because the heat can't escape from the ends. So it's always going to increase. If you're heating the rod, the ends are always going to increase in temperature because they're insulated. It doesn't mean that the temperature is not going to change. That's a common misconception with insulated. So because we never reach an equilibrium, we have no steady state value for this. So that makes the problem a little bit simpler because we don't have to find a steady state solution. However, we now have to deal with partial derivative boundary conditions, right? Because the temperature gradients are going to not be changing, right? That's what the partial derivatives mean, right? The gradients. So when we're doing this, the partial derivative of x of 0t is going to be 0. And it gives us a length of 40, 0, right? Now the initial condition it gives us of I'm going to kind of go through these first steps a little fast because we should be familiar with them by now. It tells us that this is 1/4. We can worry about that later. I'm going to go through the whole problem with alpha squared, and then I'll plug that in at the end, probably. So let's go ahead and separate the variables. We know the heat equation is step 1, right? Sorry, my pen's acting up. Alpha squared uxx is equal to u of t. And we define u of x of t as being x of x, t of t, and then so now let's go ahead and separate. Remember, uxx is x double prime t, u of t is x t prime. So then that leaves us with x double prime t equals xt prime. We want to move the x's and t's over. We want to move the alpha squared over to the first order side. So those are going to go with the t's. Right? We've done all this before, right? So then we're left with two ODEs, lambda x. Jeez, I'm getting a whole bunch of notifications. Okay. Minus alpha squared t equals 0. Sorry, I'm pausing a lot here. Boundary value problem. We have to redo it, right? Because we have derivative boundary conditions. So we're gonna have, when we rewrite our boundary conditions, we're gonna be left with. I'm not gonna worry about going through all that. You know how to do that. It's the same exact process. Right, we're left with this. We know we have to use our second order ODE for this. Let's start with the case when lambda is greater than 0. What would that leave us with? Well, first of all, right, and then that will leave us with, well, man, I took a little break and now I can't freaking think. Okay. Alpha squared x. I'm just gonna do it out. Why not? So then we're left with come up to here. And then we have the first boundary condition. I'm doing this kind of fast because we know how to do all of this. We get C1 equals C2. We can rewrite x prime. I'm going to plug in for C1. And then we have x prime of 40. All right, just plug in 40 for x equals 0. So then we need, oh, I forgot the mu. Whoa. Mu. So for this one, right, you can look at this and you can be like, okay, well, you can see here that C2, we don't know what that would be, so we want to look at this portion here, and we got to think what would make this 0. Well, if mu is 1, if mu is 0, that becomes 1 minus 1, which is 0. So it's possible, right? It's possible if mu is 0. If mu is 0, let's go back up here. We know that x is equal to, because C1 is C2, well, first of all, if mu is 0, we look up here now, we have C2 minus C2. Sorry, I explained that kind of poorly there. you think of it like this. So then you can see that C2 has to be 0 and mu has to be 0 from that. And because of that, we know that we're left with, well, first of all, we don't even need to care about the mu is 0 part. We can already look at this and be, oh, C1 equals C2 and C1 is also 0. Right? So then we know that even if you have this, this just further proves our point. Oh wait, C2 e to the negative mu x. Even if you plug in 0, we're going to be left with, and they're both 0, so it's always going to be 0. So it's always trivial. We don't want that. So then we're going to look at the next case when lambda is equal to 0. If this is the case, then this is this, and then this is this. This is an easy characteristic, right? Come up to here, we do our reduction of order shortcut. So who wants to actually do reduction of order? We just use the shortcut. All right, and then we have reduction of order is fun though. Right, and then oh, this is an interesting one, right? This is gonna be change. This is gonna change. We're gonna have a new kind of boundary value problem now. So C2 is 0, right? But you're gonna look at this now and you'll be like, oh, okay, well, you can see that x is gonna be C1, but x prime is gonna be equal to 0. So now, what do we do for x prime of L? We can't even use the second boundary condition, can we? So no matter what we use with x prime of L, it's not going to give us any information. So we can't solve for C1. So what we do is we're going to say that C1 can be any value. Can set as any value greater than 0. We had nothing telling us that C1 could be 0, so it's going to be any value greater than 0. So we can set it as 1, right? It doesn't matter what we set it to. It really doesn't. At least I don't think it does, but we're going to use whatever is easier for us, which is 1. So then that tells us that x naught is 1, and this is when lambda naught is 0. Notice how I'm using knots. I'm basically setting n to be 0, right? You can imagine this part's not going to be inside of our summation. So then you can also imagine this problem is probably going to be the first problem where we have to actually solve for a naught, right? So you should make that connection. We'll get to that in a minute. So lambda less than 0. This has to be negative. And then we have plus mu squared, x equals 0. And then we're left with, that's going to be negative, so. That's complex. We use our Euler's formula. I'm going to use the shortcut. This one we're familiar with how to do. We've solved one like this before, except that we have derivatives now. Negative mu C1 sine mu x plus mu C2 cosine mu x. X prime of 0 is equal to negative mu C2 is equal to 0. That tells us that C2 is equal to 0, right? Cosine of 0 is 0, cosine of 0 is 1. So I did that quickly. Oh wait, that's not negative. I did it too quick. C2 is 0, regardless. I have enough space here. So this should just be one line. Negative mu C1 sine of 40 mu is equal to 0, right? Because that whole other term goes to 0. And we just plug the 4D in. Now this is not trivial. You can tell because wait, why? Because we know that this 4D mu can be rewritten as any n pi, because sine of n pi is going to be 0. So we're going to get a value from u. It's not going to be 0. If it was 0, this would be trivial. Right, for sine, this is for sine. Any n pi, sine of n pi is 0. So then mu is equal to n pi over 40. We've been through all this before, right? You should know how to do this. And then we get our eigenvalues, eigenfunctions. I'm going to make like a little table here. We have lambda naught is 0. We have lambda n equals, this is negative mu squared. Oh, wait. Wrong one. Oh boy, this should be x of n. X naught. This one, negative n squared, pi squared over 40. This one is 1. This one was, we're left with c1 cosine mu x, cosine mu n pi over 40 x. Right? And these two are for any 2, 3, so on, greater than 0, right? So on. Okay. Step 3. Solve for t. Good old first order separating variables, right? So let's write down the first order equation here. Let's go ahead and rewrite this one. Move some things around. Integrate. Those are both constants. We add our constant of integration because these are both two definite integrals and c does not cancel. And then we exponentiate both sides. E to the lambda, that's not lambda, alpha squared lambda t times cn, yep. So then we can write out our t naught and our t sub n. When this is, so our lambda naught is 0, we have t naught is equal to c naught, right? E to the 0 is 1. When we have this, I think it was negative. Yes. I squared that, right? Oh boy. And then when that's that, this is, just plug this right into here. Times t. And then step 4 is, sorry, hold on, my night mode turned on. Okay. Step 4 is the fundamental set of solutions and the general solution. In this case, we have to define u of n and u of naught. So we know u of n, since we define u is equal to x of x, t of t, u sub n is equal to x sub n of t of x, sorry, t of little t. I'm just going to write it like this. U naught is the same kind of logic here. That allows us to write this. Now we can just plug in into here. I'm plugging t in first. I don't know why. Let me do the other one first. lambda squared. Oh, I forgot that. Wait. Whoa, I forgot the e. Holy crap. Okay. Negative alpha squared, n squared, pi squared over 40 squared. Okay. Now what? Well, we also have this one. Right? That's easy. Easy peasy. And then we have to combine our general solutions. So for the general solution, like I said, we have to combine u sub naught and u of t. So then our u of x of t, that's to make our u of x of t, right? So this is where the Fourier series is going to shine, right? So we know that if you remember back to the general solution for Fourier series, the first term is divided by 2. Sorry, this would be an n. Don't know why I wrote t there. So we're going to write down our constant. So this is like c naught over 2. We're going to divide by 2. Plus n equals 1 to infinity. C to the n. I want to write the e term first. Times t. Wait. I knew I forgot it somewhere. Times cosine n pi x over L, which is 40. Right, so this is our general solution. Now we just have to find C naught and Cn. So to do that, first we're going to use our initial condition, right? Initial condition in Fourier series. I think I remember what it was. Was it x times 16 minus x? 16 minus x over 30. And that's equal to c sub naught over 2. Remember, we're plugging in 0 in for t, so this is going to simplify. That becomes 1 times cosine n pi over 40. Oh, x over 40. Right? So we can see here we have a Fourier cosine series. Even. That's an even series, right? So let's find a naught. I might as well do the integration. I'm this far, right? I was thinking of just skipping to the answer, but might as well do it, show it out. So for a naught, why is that still red? A naught. What's the formula for a naught? I'm forgetting. I'm sorry, c naught. But that's a naught in the Fourier series, right? I'm trying to remember. It's just the integral of f of x dx, right? I think it is. Yeah, and I'm going to actually rewrite the f of x here, because I think I can simplify that out. That's just 60x minus x squared over 30, which is just 2x, x squared minus, yeah, that's just 2x minus x squared That's an easier way of looking at it than that whole big thing with fractions. Ew, right? So then C naught is remember, it's the integral negative L to L f of x. Is that it? F of x dx? I want to pull up my old notes. I think that's it. Yeah, that's definitely it. Oh, I forgot to explain why the divided by 2 comes from. If you watch my derivation of the Fourier series coefficients, you'll understand where that divided by 2 comes from. It's a more in-depth kind of explanation as to why it's there. That you should just watch that video to understand. For now, just pretend like it magically appears, that it has to be there. It's always going to be like this. You know, you don't have to worry about like too much where it comes from. It's just the way it is. You'll see, if you watch my derivation video, you'll see that. A lot of times people will keep it as C naught, but what they'll do is in the formula, they'll divide it by 2 in the formula for C naught. So you might see that sometimes. It's just that 1/2 is always going to be in there. I just prefer to write it like this. That's just what I prefer. Okay, so we might as well, since this is an even series, that tells us that f of x is going to be even. We can see that it's even, but well, we don't know that it's even. Okay, so it's even, and we know f of x is then going to be even. So then when we do this, we can go from 0 to 40, multiply the whole thing by 2. All right, and then we have 2x minus x squared over 30. That's not a bad integral to do at all. That's going to be, let me see if I can, I'm going to do this by myself. Oh, I forgot to divide by, oh, I forgot. It's 1 over L times that. So this is 1 over 20 times integral, well, this is x squared minus x cubed. What's 30 times 3? 90. From 0 to 40. Okay, I'm going to need a calculator for that. Let me write it out. All right. So that's going to be, oh, let me get my calculator. Where's my calculator? No. I'll be right back. Okay, let me see. So 40 squared. Might as well divide by 20 while I'm at it. 1600 divided by 20 is 80. Minus 40 cubed divided by 90. Oh, did not put that in right. 40 cubed divided by 90. Is all of that divided by 20, which is 320 over 9. Okay, 320 over 9. Which is, we do 80 minus 320 over 9. That is 400 over 9. So that's our A naught. Not the nicest number. I'm sorry, C naught. Holy, I'm so used to my Fourier series notation. It's the same thing. So Let's look at C sub n now. I almost said A sub n. Remember the formula is 1 over L, negative L to L, f of x. This is the cosine term. So, whoops. This one will be, we can multiply by 2 again, go from 0 to 40, f of x, 2x minus x squared, times, as a cosine, n pi over 40 times x. This one's obviously annoying. I'm going to split this into two integrals. Oh man. Oh, I'm so tempted to just skip to the answer. I don't like that x squared. Well, we can do this. I'm actually going to pull out the 2 on this one. It's 0 to 40 x cosine of n pi over 40x minus 1 over 20. Wait, I'm missing something from that. Oh, I like how I caught myself down here. Wow. I was going to say, where's that 30 from? Where's that 30 go? What's 20 times 30? 20 times 30 is 600. Negative x squared, negatives out there. Cosine n pi over 40x. That was not too fun. Okay. For this one, use x, du is dx. V, dv is cosine n pi over 40x. So then this is 40 over n pi sine n pi over 40x. For this one, we're going to unfortunately have to do 2 times. That's cosine, sorry. This is going to be the same thing as the other one. Uh, 40x, yes. Okay, where was I? Okay, let's just go ahead and do this. So we have, for this first half, we have 1 over 10 times UDV, or UV, sorry, 40 over n pi x times sine n pi over 40x minus, no, from 0 to 40, minus, I'm going to pull out that 40 over n pi, it's v du sine pi over 40x, whoops, dx. And I'm going to make 2 lines. This is the first one. The second one is going to go down here. It's minus 1 over 600 times 40 over n pi x squared sine. I encourage you to do this with me. Do it by yourself and see if you get the same thing I do. 0 to 40 minus pulling out the 40 times 2x, so that's 80 for n pi integral 0 to 40 x cosine. Oh, sine. It's v. Sorry, I looked at dv on accident. Okay, so good thing I caught that. This looks right to me. And then we can finish up that, we can simplify that first half a lot. What is 40 times 40? You know what? I'm just going to leave it like that. Well, wait a minute. No. It's 0. Because look, I almost forgot about the trick. Sine of n pi is 0, right? Because 40 over 40 is 1, so that's sine of n pi, 0. And 0 sine of 0 is 0, so that term goes away. I actually really like this one here for a reason. Part of it's gonna work, but part of it's we're gonna make some nice simplifications here. This isn't gonna take much longer. So let me just do it quick. We're gonna be left with. We still have the second half here. That one is gonna lead us somewhere. This is from 0 to 40, by the way. I forgot to write that. That becomes, what was that? That would be cosine. That's negative. Yeah, cosine. N pi over 40. X from 0 to 40. Okay, and plus or minus. I have an idea. Let's not do that yet. Let's go back to this. Let's do this again. It's kind of cluttered at the moment, but yeah, these are. I crossed off the wrong one. Holy crap! It's still the same thing though. You get what I mean. Cosine, right? That'd be negative. Cosine n pi over 40. X. Yeah, okay, so then I'm thinking right now. Because we still have that negative 1 over 600 times that, so it's still going to be plus. Oh, that's an ugly number. Yeah. I'm not going to be able to fit this all on this end, or am I? Okay. This is kind of cluttered, I'm sorry. Over n pi uv from 0 to 40 plus v du. It's minus, so it's plus. I'm pulling out the 40 over n pi, integral 0 to 40. Oh boy. Integral 0 to 40, where was I? Cosine dx. And we're almost there. You'll see this is the integral of a cosine, which ends up being evaluating a sine, which is going to be 0. The sine of n pi is 0. So I'm thinking ahead here. These other two are going to evaluate to something, unfortunately. Let's get rid of that. That's going to can multiply those 40s together, I guess. That's going to be negative times a negative. That I know is 1600. Pi squared cosine of n pi minus I'm thinking right now. Because cosine of 0 is 1, so that's still 1600. So that's minus 1600. Because it's a minus, and then the two minuses is plus, so it's minus. A lot of sign things going on right there. N squared pi squared minus here, let me think about this. What's 800 over 6? I'm sorry, 80 over 600 times 40. Oh, whoops. Times 40 is 16 over 3. What if I don't? What's 80 over 600? 80 over 600 is 2/15. Wait, why did I put a minus right there? What was I doing? Why did I just do that? I have no idea. Okay, times that'd be negative 1600 over n pi times cosine of n pi, and the other one's going to be 0. I just realized something. See this negative 40 here? I completely forgot about the negative that's there. Well, no, I didn't. I don't know. Why did I change that to plus? I'm so confused. So my notes are what's going on here? My notes is differing from what I'm doing right now. I've been checking what I do every step. What I did here is differing from what I have in my notes by one sign error. So I'm gonna pause and see what I'm doing wrong. All right, so I can't see anything wrong with what I've done here. I think I messed up in my notes. Somehow I turned a positive into a negative. I have no idea what happened there. But I'll just keep going with what I have here. It's just a sign error. It's 160 over n squared pi squared. Which we can rewrite this as negative 1 to the n. It doesn't really matter for this problem. It's a very small simplification. If we had something like, oh wait, we do. Well, oh, this is actually very interesting. Let's not change that yet. I see something here. Oh, we're good. I just made a simple sign error in my notes. That threw me off. But my next step in the notes was actually correct, though. I don't know how I ended up... Okay, I don't know. Maybe I just threw that in there to confuse myself right now. I trolled my future self. Alright, so we have 80 times... Well, 80 over 600 times 1600 is 640 over 3. Right? Okay, so now, the reason why I didn't pull out the 1600 and the 160 over n squared pi squared, and you can rewrite that term over there for even and odd n. You can actually simplify this without, first, what I always recommend doing is writing it fully out. Because see how we have 2 cosine n pi's, we can combine these two terms. This term and this term we can combine. Like, what's 160 minus 640 over 3? Is negative 160 over 3. So our c sub n, this is going to be our final answer. Now, of course, we can rewrite that cosine too if we wanted to. It really doesn't matter. It's a small change, right? I would say we wouldn't rewrite it. Like for this, normally you can leave it as cosine n pi. But like if we had like take out the 160 and you have the cosine of n pi minus 1, and then you have negative 1 to the n minus 1, you can simplify that. But then yes, that's a worthy simplification. But this one, you can kind of keep it as cosine n pi if you want. It's just really personal preference. I like to write it out like this because it looks cleaner than having cosine. Alright. We know, I wrote that down again because we know that that's that. So then we can go ahead and plug that into our final solution. So what's our A naught? I mean our C naught. 400 over 9. Remember, it's divided by 2, so it's 200 over 9 here. Minus sum n equals 1. 200. I better write smaller because this is going to be kind of long. Sum 160 over I pulled out the negative, by the way. I can also pull out a 1 over pi squared from that. Well, no, I can't, because we still have the other two terms. No, I could. But I don't have to, though. Here, let me just do it. I can pull out a 160 over pi squared. Yeah, let's do that. So minus 160 over pi squared. Because now the whole inside will be positives only. And this will be once. I just took that out. It'd be cosine of n pi. Yeah, you know what? I'm not going to simplify it down because I think there might be a chance of simplifying. I don't know. I'm not too sure. I'm just going to keep it like this. Maybe it can't really be simplified, I don't know. It's possible this might be able to be simplified further. I'm not too sure. But I'm going to keep it like this. We can't take out that 3, though. That's not something we can take out. That becomes 1 over n squared times, this was e, I think I remember what this was, pi squared alpha squared, which alpha is 1/4. So that's 4 times 40 squared. What's 40 squared times 4? 6,400. Times cosine. And that is correct. That's what I have in my notes. N pi x over 40. This is different than what I have in my notes. Oh, I didn't pull out the 160 over pi squared in my notes. Oh, I forgot the t right here. Okay. Everything else is right, though. Bam. That's the answer. So that was a little bit longer of a problem, right? So now, of course, if you were to solve one of these, you might have one end that's insulated, one end that's not insulated. If you had a case with one insulated end and one non-insulated end, you're gonna have an interesting situation. I'm not gonna do a video on that because I never did it myself, to be honest with you, with heat equation. We'll look at it for the other equations. Especially I think the wave we'll definitely look at. But I think you would have a steady state solution because you would have one end that's allowing heat to flow out. So eventually, I think it will reach equilibrium, right? Because it kind of makes sense that outflow on the one end will still like be able to balance the heat generated inside the rod. I think so. The temperature will kind of reach equilibrium eventually. So there's also some cases I think where like you can have boundary conditions where you have like if I don't know if you remember my Newton's law of cooling video when we looked at like what's the temperature like if something's this temperature, it's placed in a room that's this temperature. What's the temperature at this time? Like you can have a boundary condition that has like a convective condition that's kind of like that. It's like convective, which is basically Newton's law of cooling, like a boundary condition. And like you'll have like your ambient temperature, you have to worry about like you still have to deal with the steady state solution for that case, and you're going to have a more complex math basically. But it's basically a similar process. Like I've seen a problem that's like that in a more advanced math class that I've had. That's what I'm trying to say here. But I can't imagine having to worry about that for standard DiffQ class. So I'm not going to worry about it. That would be a very long video to do. I'm not too worried about that. It was actually very nice in my advanced like PDE class. We had we were given tables for integration. So like all this integration here we could have did in one step, which was nice. That was a nice thing they did, but the problems were a lot harder, though, But yeah, that's that. So that's the end of heat conduction. Obviously this is ideal cases. In real life, you don't have these ideal cases necessarily. You don't have a perfect rod, under these perfect conditions. This is just a demonstration of PDEs. If in normal life, typically you have nonlinearities, which make solving them like impossible without approximating. So usually you approximate in real life. If you ever think of fluid dynamics and you get to Navier-Stokes, you'll see a lot of that with nonlinearities. Yeah, let's move on. Enough about that. Let's move on to the wave equation. So I'll see you for that.